Very good morning to all of you on the day 3 of our Gyan course on chalcogenide-based phase change memory for non-volatile data storage. So now we are going ahead with our session. So now I request Dr. Henry to proceed with this talk. Thank you.
Okay, so we will continue our lecture, and today we will look to the chemical bonding of phase change materials. This is a very important topic and very interesting topic because the bonding, as you know, the bonding in the materials, they define the properties of the materials. Can you hear? It's okay? Yeah, okay, it's on, it's on. So, now let us consider some typical substances. For example, silicon dioxide. It exists in amorphous and crystalline form, and as you can see, it shows it's transparent in both states. So in amorphous, it's transparent, and in crystalline. So these are so this is here can be also nicely seen in the transmission measurements. So both crystalline and amorphous, they are transparent. So there is no property change on phase transition between amorphous and crystalline. So it can exist also. So you see here there's a single crystal found in the nature. It's also transparent. And this is, this is silica again. This is this balls, small balls. These are amorphous and these are also transparent. Let us look to our phase change materials. If we take amorphous, for example, germanium telluride, and make a thin film on it, like 100 nanometer, we see that it's transparent because if you put it on the sheet of paper and write a letter like A, and we put it, I have deposited it on the glass, you can see that you can see the letter A. However, if we crystallize this germanium telluride, then it transforms to the crystalline phase, and now the properties here has been changing, and now this germanium telluride is not more transparent. Here we can see also nicely it's in the transmission measurement, optical measurement. So this is the amorphous state, and this is crystalline state, and you can see that the amorphous state is more transparent than the crystalline state. So what we can see here that the phase change always change their properties in crystallization, while ordinary covalently bonded materials, not like silicon dioxide. This can be also nicely seen in other measurements, like in the ellipsometry, using ellipsometry, if we measure the dielectric constant, the dielectric function, epsilon. We can see also that the amorphous phase change materials with different composition. Here, this is going from germanium telluride to the different, and also AST. They have lower the dielectric function compared to the crystalline phases. If you go to the crystalline phase, you see that the dielectric function, that specific energy, they are much larger than for amorphous material. So this property of this dielectric function is covered by the electron polarizability of the valence electron. And this valence electron, they define the bonding in the materials. So large epsilon for crystalline materials than for amorphous. Also, you can see some change in the properties if you use so-called atomic tomography. This is also the famous method to measure chemical composition of your material, also make 3D chemical composition of your substances. So here the also phase change materials, they are also measured, and here we should consider two processes which can occur in this atom tomography. So how it's measured, you have a very sharp tip made by FIB of your substance by phase change materials, and then you apply here laser pulse to that, and some current to heat it a little bit, and then you can like extract the atoms from this sharp tip, which goes to the special detector. And here we can distinguish several processes, mainly two. One is called PMI, this is high probability of molecular losses, and this is the second PME, this is the high probability of multiplied events. And if you do such measurements for different materials like covalent and metallic, and also our phase change materials, which are seen here, we see here that so PMI is not much change within the solids. But if you look to the second process like PME, you can see nicely that covalent metallic, they gives you only 20% of this event, and the phase change materials, they are seated here, so they show much higher PMI event than normal covalent or metallic solids. And here, this is also a nice technique because it shows you the rupture of bonds. So to extract the atoms here, you need to destruct the bonds between the materials, and then they can fly to your detector. And so here you can see that there is somehow differences in different materials, like phase change and covalent and metallic bonded because of different bond rupture. So crystalline GST shows PMA like 65% and amorphous GST less 22. So there is somehow difference even between amorphous and crystalline material. So they are also differently bonded. Let us look to some properties, like main 5 properties, or to differentiate the chemical bonding mechanisms in solids. So the first, this is electron conductivity, which is electrical identifier. Second, effective coordination number, this is structural identifier. Then electronical polarizability of valence electrons, this is sigma epsilon. This is optical identifier. More effective charges, chemical bond polarizability, Grunheisen parameters, and ionicity. Now if we take some materials like ionic, covalently bonded, our phase change alloys, and metallic, and if you look at different properties, we can see that this is we compared it for crystalline phase change materials, not for amorphous. So what we can see here that phase change materials, they have first property is electron conductivity. They have moderate electron conductivity, so it's like between a little bit larger than covalently, but smaller than for metallic. Structural identifier, so they do not satisfy this rule for coordination. And this is number of S and P electrons. So for electron polarizability, they have very high electron polarizability, as we have seen. The other shows ionic low or covalent moderate. The metallic, they not normally applicable to this. Born effective charges here for ionic it's low, for covalent moderate, and again for PCM high. This parameter, Grunheisen parameter, for ionic is moderate, for covalent low, and for PCM again high, here it's low. On the ionicity, somehow it's like on the order of covalently bonded material. PCM, as you can see here, like for germanium telluride, it's 0.2 silicon dioxide, it's also on this range. So what we can see that we have large values of electronic polarizability, chemical polarizability, Brunisen parameters, structural identifier, which is not satisfied, but ionicity, which are similar to the covalently bonded material. But overall, in general, we see here that there is a huge difference between this ionic covalent bonded and metallic bonded. So now also let us look to some other identification of materials bonding nature. First we will look to the electron localization. We studied already it with, we know from yesterday some properties of phase change materials, that on the phase transition the electrons more delocalized, so it will be localized in trigonal phase delocalized, and it shows metallic conductivity. And so let us look to the covalently bonded material like diamond and silicon. So here electrons are localized near the nuclei and the bonds between them. For ionic materials, electrons are localized mostly near the atoms. For metals, less valence electrons per atomic number, electrons are delocalized and linked to electronic conductivity. And here we see that there is electron localization in amorphous and cubic GST, and electron delocalization in vacancy order and trigonal GST. So second parameter identifier, this is atomic coordination or coordination number. So in metallic elements, they have this NC8, like for body centered cubic, and 12 for cubic or hexagonal. In covalently solids, NC poses 8 minus n rule. For metal, this is larger than 8. But for phase change materials, it's like in between of 4 and 8. So these rules are not satisfied. Again, we see here differences between different bonding, especially for phase change alloys. At the summary, what we can say that the phase change materials possess a unique bonding mechanism. The characteristics of this mechanism are between those of covalency and metallicity, but distinct different from both. And these materials can be referred like metavalent solids or incident metals or bond change materials, since amorphous GST is simply a covalent material. So I will start with bonding. So phase change materials, they have unique bonding mechanism, and the difference from other solids. So now let me continue with our lecture on impact of dimensions on material properties. From our lecture 1, we have already defined the melting current, and we know that if you reduce the size of the phase change layers, we can also reduce the melting current. And so also if you reduce the heater size, you can also reduce the melting current, but this is mainly on the device side. But anyway, if we shrink the size of our material and device, we can reduce the melting current. So in this part of my talk, I will consider the size-dependent properties of phase change materials like nanoparticles, nanowires, and thin films. And I will also consider the impact of this of the material size on PCM device performance. So now, before to start with phase change materials, I would like to make some definitions. What are nanomaterials? and what type of sizes exist and what properties can be changed in nanomaterials. So first, the nanomaterials are materials with less than 100 nanometer size, at least in one dimensions. We can classify these materials like 0D materials, 1D-dimensional materials, 2-dimensional materials, 3D-dimensional bulk nanomaterials. In 0-dimensional materials, all 3 dimensions of the nanomaterials are on the nanoscale, like if you look to the nanoparticles. In the 1D nanomaterials, in any one dimension it will be nanoscale range, but in other 2 directions it remains out of the nanoscale range, can be or can be stay in this range. These are nanorods, nanotubes, and nanowires. 2D materials, here we have any 2 dimensionals in the nanoscale, and remain in 1 dimension is out of it, like nanofilms, nanolayers, and nanocoatings. 3D or bulk nanomaterials, here in any dimension these nanomaterials are not in nanoscale range, so in 3 dimensions they are larger than 1 nanometer, 100 nanometer. It could be materials like nanocomposites, core shells, multi-nanolayers, bundles of nanowires, etc. So how the size can impact, or which properties can the size impact in materials, which physical properties can be impacted by the materials. So here science-dependent properties, they can influence the thermal properties, like melting temperature. They can influence optical properties, like absorption and scattering, electrical properties, currents, mechanical properties, and magnetic properties. For us, we are interested mainly in these 3 thermal properties, optical and electrical properties. And here I would like to show you one example. Maybe you know about this Kim Lazarus cup. Here it's made of dichroic glasses, and it shows different colors if you reflect the light or if you transmit this. And these glasses, they made of nanoparticles of gold and silver. So it's a very nice example to see how the size of materials change the properties of like solar like carbon. So now let us look what happens if we shrink the properties of our materials, like semiconductor, so we can get some novel properties, for example, optical properties. Here, this is one sketch. It shows you what can be changed here in the case of nanoparticles. So if you start with the bulk materials and go to smaller size, we have here the increasing of the band gap. So for bulk materials, we have low band gap size, and if we decrease the size of the semiconductor nanoparticle, we can see the increase in the energy band gap. And also we can see the splitting of energy levels, and this all happens due to the quantum confinement effect. So the band gap increase with decrease in size of the nanocrystals. It also, this change in the band structure, band diagram and structure, it also influences the properties of the nanoparticles. So here you can see the size-dependent optical properties of such nanoparticles. This is the fluorescence emission. It was measured in the liquid. And this is the first sample, this is the 8th sample, and you can see the change, the shift of the absorption from higher than larger wavelength to the lower wavelength. So we have here so-called blue shift. And so by control the size of such nanoparticles, we can control and tune the color light of such materials. So now let's look, for example, the impact of size on properties of standard material like silicon. So silicon is a famous material for industry, for microelectronic industry, and so there was a huge research in this direction, and many different nano objects can be produced, like nanofilms, nanowires, and nanoparticles, and they all show different properties as to bulk materials. First, it was found that the dielectric constant changes the size of silicon. Here, this is the nanoparticles, and here this is nanofilm. So we see the reduction in the dielectric constant. Then the melting point is also changing, so it increases for nanofilms, nanowires too. And here the crystallization temperature changes also for silicon, the thickness, thin films like the thickness less than 20 nanometers, and it can be calculated by this equation. So we can see that even for that we can see that the material properties changes to the size. And now let us look to the how this reduction, shrinkage of the size in the case of phase change materials can influence its properties. So first of all, let us look how these objects can be synthesized. We will start with 0D objects like nanoparticles. These nanoparticles can be synthesized by different approaches. One is very simple and widely used. This is chemical synthesis, colloidal synthesis. Here you can produce amorphous germanium telluride nanoparticles with tunable nanoparticles diameter down to 1.8 nanometers. Also, you can use magnetron sputtering, inner gas condensation using nanoparticle deposition system. This is a special system. And so you can here produce also amorphous germanium telluride and GST2 to 5 nanoparticles with diameters which can be to reduce until 9.4 nanometers, and for GST to 4.7 nanometers. Here also you can use polymer lithography using like special balls, polymer balls, and you can deposit there this nanodots, produce nanodots, and here you can produce the nanodots of germanium antimony, GST2 to 5 and AST, and here the size of such nanodots can be less than 50 nanometers in diameter, and the spacing between them can be like 50 nanometers. So here you see that such nanodots can be produced on a substrate by a self-organized process, self-assembly process, self-assembly. So now let us look to the crystallization and melting temperature of such nano objects. Here, this is the dependence of crystallization temperature on the germanium telluride diameter. And here what we see that the crystallization temperature of germanium telluride nanoparticles is increasing, it's decreasing of size of these nanoparticles. So it starts from bulk here somewhere, and then it goes until almost 400 degrees C. So this is a huge change, because the bulk crystallization of germanium telluride is like on this range, 180, close to this 160. Then the melting temperature decreases with increasing the size of nanoparticles, and crystallization temperature increases, can be also seen here. And so these properties, like the increase of TC, should lead to improved data retention and room temperature, and the decrease in the melting temperature. It shows it should influence the power consumption of our memory cells. So here, these authors, they also did some estimation on power consumption of such nanoparticles. So they use this scheme device like electrode oxide substrate and this germanium telluride, and they use this equation to calculate the power consumption. Here this is Cp, this is specific heat of germanium telluride, and this is the mass of spherical germanium telluride. TBT, this is the temperature, the crystallization and melting temperature, and here new loss, this is the power loss due to the heat dissipation. And what they found is that there is also a reduction of crystallization temperature and the melting here. So on melting or on crystallization, the reduction of power consumption. So they can be potentially used for low power phase change devices. But also, what is also interesting, that the phase change nanoparticles, they show dependence of properties, crystallization temperature, melting temperature, but in another way as a normal other materials. So here we have increase of crystallization temperature, but normal nanoparticles of our substances, solids, they showed in another direction that the TC of nanoparticles is lower than of bulk material. Here we have another effect, like a reverse effect, decrease of crystallization temperature compared to the bulk in other materials. It's in our way, so we have reduced crystallization temperature. So now we also can look to the other material properties like viscosity and temperature dependency of crystal growth rate, and also crystallization activation energy. So if you look to the temperature dependent viscosity, these are the nanoparticles of GST and germanium telluride. So the germanium telluride, it shows this M value like 78, and thin film like also on this range. For GST it was measured a little bit low for nanoparticles, for thin film a little bit larger. So here they found that there is a strong fragile to strong crossover for GST nanoparticles, but not for thin films. The crystal growth rate actually changes in another direction. So for germanium telluride nanoparticles, it's a little bit lower as for thin film, and for GST 2 to 5, it's on the range as of thin film. So crystallization activation energy for GST 2 to 5 nanoparticles, it's like on this value 2.2 for size 16 nanometers, 2.4 for 17. For thin films, it's also, they have also this value, so there is not a large difference. And for germanium telluride, so we have crystallization activation energy on the average of 4 nanometer, which is a little bit larger than for GST 2 to 5. So now let us look to the optical properties of germanium telluride nanoparticles. So here the UV absorption spectra for germanium telluride nanoparticles are shown. So first, these nanoparticles were produced as amorphous and then crystallized. So this graph shows you absorption against energy, and here for amorphous nanoparticles, and the size of nanoparticles changing, and the absorption is also changing. So here we have more absorptive nanoparticles than these nanoparticles. So this also leads to the change in the band gap, the size. Like for smaller, it's like on average 0.5 electron volt, and for larger, this is 0.67. But if you compare to the thin films, which shows the band gap on this range between 0.0 and 0.85, we see that there is not a huge difference between nanoparticles and amorphous thin films. However, it's somehow interesting that crystalline nanoparticles, they showed larger band gap. Here we see the dependence of band gap on the size. So that for the smaller size, they obtained the band gap of 5.1 eV. For larger size, it's 0.8. But for crystalline GST thin film, there is reports on band gap 0.6. So this is a huge difference, almost double here, and it also changes in our way. So it's somehow reversed. Here we have increase of band gap, and here in the case of thin film system, we have decrease of thin film of the band gap value. They also studied the local structure of amorphous germanium telluride nanoparticles, and they found that such nanoparticles they possess the motif of high pressure orthorhombic phase, and this shows that the nanoparticles, they are under compressive stress. So we already know that the germanium telluride, crystalline germanium telluride, it exists, adopts the structure like cubic, rhombohedral, and rhombic, and this rhombohedral alpha germanium telluride used for phase change, in the case of phase change. So there is also a report on the production of GST nanoparticles by so-called femtosecond laser printing. This is a very interesting method. It's based on femtosecond laser, and here you have a substrate and thin film, and you irradiate your substrate here from back side, thin film on this top side, and then by moving this system, the laser or substrate, you can heat up and then produce like drops of GST nanoparticles, and then deposit on the substrate. In this case, you can produce the amorphous nanoparticles of the size between like 50 and 200 nanometers. These nanoparticles can be optically switched, reversibly switched between amorphous, crystalline, amorphous, and crystalline state. So the nanoparticles can be switched using femtosecond laser pulse, which is also interesting if you want to apply them for memory applications. So there are also reports on the device integration of nanoparticles. Here you see how the germanium telluride nanoparticles were integrated to the PCM device. So again, here you need a lithography unit, and these are different steps shown here. So first you have to produce some electrodes, then spacer oxide, then also have to pattern it and produce like here holes or pitches, and then you make drop cast of the nanoparticles, you anneal them, and then deposit another electrode, platinum electrode, to make contact between them. This is the TM image of step C. You can see the nanoparticles inside of such a holes here. So then the properties of such devices, they were tested. So they showed nanoparticles first. This shows the contacting of these nanoparticles. This is the nanoparticle thin film here with such a hole. They can produce different holes, and these are metal contacts here. And so first they studied the crystallization of such amorphous nanoparticles by applying DC pulse. So you can see here nicely that they showed the switching characteristic for different steps, and then also cycling endurance of such nanoparticles also were measured by using pulse setup. So here, if you apply set pulse with amplitude 3 volt and duration 100 microseconds, and this is reset pulse, amplitude 15 volt and 50 nanoseconds, you can see the switching between high resistance state and low resistance state for more than 160 cycles. So such nanoparticles, they show potential for the application in phase change memory devices. So now let us look to some properties of 1D objects. 1D objects, these are nanowires. The nanowires, they can be produced by using so-called VLC process. This is vapor liquid solid, but for this process you need a special catalysis which helps the nanowire to grow. Here in this case you use gold, and the nanowires like germanium telluride and GST can be grown on a substrate at a temperature of 680 degrees C. You see, if you produce such nanowires, they have sizes in nanometer range. They are long, but they are randomly oriented. By using MOCVD, which is metal organic chemical vapor deposition process, you can also produce nanowires for different sizes. Here the size distribution is much larger, as in this case. Here they will deposit at 400 centigrade degrees C. And also you can use MOCVD bottom-up approach to grow the nanowires inside of such holes here. So here you get much more oriented nanowires, as in this case, if you think about the integration of such nanowires, and they will even grow on the p-doped silicon 1100 wafer at 360 degrees C, and it was into germanium telluride nanowires. So you see different methods can produce the nanowires or phase change materials. So now let us look to some properties of such nanowires, like melting temperature and then first melting temperature. So the melting temperature of germanium telluride and GST225, it's 725 degrees C for germanium telluride and around 616 for GST225. In the case of nanowires, this melting temperature is reducing a lot to 410, and in the case of GT, in the case of GST, this is 375. So we see significant lowering of melting temperature. How to identify this melting temperature? It's also not so easy because you have a low amount of material. Here, this melting temperature was identified by using the single heating TM experiment. Here, they heated the nanowires up to up to this temperature, different temperature, and they found the material was between 390 to and more. But if you do such experiments, you should be very careful because you need to coat the material, because material can evaporate even in vacuum. This image shows you uncoated nanowires heated to 400 degrees C, like in this here compared to this. Here you have the melting. Here we have also some melting information of holes and mass loss in the nanowire. And then after coating of such GST, it was thin film. In the case of thin film, then you see the melting of thin film. It starts at 600 degrees C. Here, if you coat also nanoparticles with amorphous SiO2, then you find also some melting and sublimation, and each starts at this temperature, 470 degrees C, and it's much lower than the bulk melting temperature. So now let us look to the nucleation rate and crystallization activation energy of amorphous nanowires. Here, this is the function of nucleation rate, and the nucleation rate decreases with decrease the size of nanowires. So this points and triangles that shows the experimental data, and these are the theoretical simulated data. So they are in agreement with the nucleation. This is nucleation. This crystallization activation energy. So it's reducing. If you think about the thin film of GST 2 to 5, it's like on the range 2 to 5. And for nanowires, this parameter activation, crystallization activation energy, it's reducing the size. Also, nucleation rate, it shows the increase of the nucleation rate, the decrease of the size. Here is again there is a nice agreement between the theory and the experiments. So what we can learn from this, for example, from the nucleation rate ND, so this ND suggests faster set times for nanowires, and the activation energy suggests that affects the data retention and scale with nanowire size. So if it's 200 nanometer diameters, we have like the stability of such objects for 1,800 years in a device at 8 degrees C, and only 3 years for 30 nanometers at 80 degrees C. So you see that this actually not good for the device if the size reduced, because our data retention is also reduced for less years that's required. We need at least 10 years, so maybe for like in this range we can get the 10 years data retention. So now also some devices based on nanowires were produced, like shown here. This is the nanowires which was integrated to the two electrodes, like here, and then some switching characteristics were measured. So here what we can see first, that the pulses, 100 nanosecond pulses can induce amorphization, and 300 nanosecond pulses can induce recrystallization. It's somehow a little bit, the pulse length is a little bit longer compared to the PCM devices and thin films, but if you think about it, it's 30 nanometer nanowires device, and it's made in this geometry. So some programming currents, so the programming currents, they shift to lower currents with decreasing the nanowire diameter, the diameters. Also, there is a lowering of writing currents with decreasing of nanowire diameter, like for 30 nanometers. So here we have low writing currents. And the endurance here of such devices tested for 60 nanometer nanowire device, it was really nice. Could be tested until 10 to the 6 times, and there was a difference between high resistance state and low resistance states, like to enough for device application. So nanowires, they have also potential for nanoscale phase change memory device. But here in this direction, maybe we need more work to integrate in the real PCM device. So here there is also some results on the electrical switching on nanowire-based PCM devices. Here we have writing currents and nanowire thickness. You can see, as supposed from the first lecture, if we reduce the size of of our phase change materials, we can reduce the writing current. So for GT and GST, you can see it's nicely. So it reduces for less than 0.5 MA. Also, power consumption can be reduced with the size of the phase change material. This graph shows you the power consumption, and this is nanowire thickness, again GT, GST, and the small size nanowires, they show significantly lower power consumption, and the GST225 show low power consumption compared to the germanium telluride nanowires. Here, recent currents also have been measured independence on the contact area. Here you see the nanowires, and here the thin film, and here we see the dependence of the recent currents for the nanowires. Generally, it's more than as for thin film, but if we approach very low contact area here, then there is only a little bit difference, not a huge difference in the recent current. So you can also think if you produce very thin film, let's say 20 or 30 nanometers, and if you look at it in one direction, it can be represented like a nanowire. So with the reduction of thin film size, we can also get similar properties in the recent current as for nanowire. Also, resistant drift was measured for nanowires, and it's also a function of the size. So if you start here for larger sizes like 100 nanometer, and if you reduce it to the 45 nanometers, you can see that the value of resistant drift, this is alpha, it reduces a lot. So here we have the value of 0.009, here 0.00. So we see also the scaling of resistant drift with the material size reduction. So now let us look to the 2D materials like thin films, and let us look at their crystallization properties. So for thin films, as for nanowires and nanoparticles, there is also dependence on the crystallization temperature. So it increases, the size decreasing. Here, different materials were tested: germanium antimony, AST, GST, nitrogen doped GST, antimony telluride, and they all, these compositions, they show the reduction of the increase of crystallization temperature with the reduction of thin film thickness. Also, there is a reduction or increase of initial resistance of GST with size decrease. Here we show this is the initial resistance, and this is the size of our thin film, like 2.5 nanometers. It's like here in this range. Here this is 5 and 10. So you see, and for thicker thin films like 50 nanometers, the initial resistance is a little bit like 3 orders of magnitude lower compared to the nanoscale thin film. Also, there is a reduction of melting temperature with the size. This is for germanium telluride. Here you see that the melting temperature, this is bulk, and this is the thin film. So crystallization activation energy against the thickness, it also reduces, it increases with reduction of thickness. Here, if we have 20 nanometer, it's like close to the bulk value, and then it's increasing due to the value of 4.7. So also some properties, structural properties. Here, this is about the oxidation of thin film. So if you want to study such a really thin film with thicknesses between 1 and 2 nanometers, so you have to cap these thin films by a layer like aluminum oxide or another layer to prevent oxidation. But this capping layer, it can also impact the crystallization of your material. So it's good, but let us look how this layer, capping layer, affects the properties of thin film, nanoscale thin film, like of GST between 2 and 10 nanometers. So here, if you have it, and if you deposit some capping layer of titanium nitride or another typical capping layer, zinc sulfide, silicon oxide. So what happened here? That depending on the type of capping layer, we have also increase of crystallization temperature of GST thin film here, as you can see. And also there is also some negative effect on the TC of GST if you use this layer. So what such protective layer make with GST thin film? They use some stresses, compressive stresses to GST thin film, so they compress it, and the stresses can be really large. In this case, this is 60 MPa and this is 240 MPa. Anyway, so the 2 nanometer amorphous GST films, they can be recrystallized independent of the stress of protective layer. And also they found and discussed that the TC, increase of TC, it originates from the compressive stress induced by protective layer. So they claim that it's not only the effect of the size, the increase of crystallization temperature, but also the protective layer might also impact the crystallization temperature. Some data. This is very old data on the crystallization rates of such films. Here, this is the stack, the phase change materials in different layers. This is like used for optical devices, like for DVD or CD. And here these layers, like metal mirror layer, dielectric layers, they have this fixed size, 20 nanometer. This 100 nanometer, and the size of phase change layer has been changed. And this shows that if you make experiments on the crystallization time, it's shown here. If you change the thickness of phase change layer, you can see that the crystallization times, they are increasing. So somehow the crystallization speed of GST it increases with layer thickness, while it decreases for AST. It seems to be that some such interfacial layers, they also impact the crystallization time of GST films. So there is also impact of the size on the optical properties. It's also it's measured for amorphous and crystalline thin films. The first here curve it shows the GST1 to 4 with the size of 7.5 nanometers. This is the 33 nanometers, and you can see that the transmittance of GST increases with decreasing of the size. Also the same effect on transmittance observed for crystalline materials. Also for amorphous, this is refractive index N, and this is excitation coefficient K, and all data shows the change of the properties, the increase of its properties, the decrease of the size of GST film. So the optical parameters are thickness dependent too. So some also properties of nanoparticles in film. So such nanoparticles, for example, germanium telluride nanoparticles can be synthesized by chemical method, and then here these nanoparticles can be also formed as a thin film by dispersing it on the substrate, like shown here. This is silicon oxide. Amorphous germanium telluride nanoparticles on the substrate, on the silicon dioxide, and this is crystalline. So they form here thin film. So the size distribution of such GT nanoparticles, this is in this range, like 6 nanometers. And so what happened here with such nanoparticles with such small size, that the band gap of amorphous material is much larger, 1.4 eV, and this is for crystalline such nanoparticle thin film, it's somehow again here it's reducing. It should be for thin films. Before, in previous slide, we saw another effect, a reverse effect, that the crystalline nanoparticles, they had larger EG than amorphous. And here we see also increase in the band cap for nanoparticle thin film, for amorphous, for here this is real thin film, it shows like 0.8 eV and crystalline here 0.6. Here this is also difference up to 0.2 eV. Also this thin film show optical properties like they have a larger N and K here, and if you look to such radar, it calls like figure of merit. Here we have delta N, which is shows include N and K, and which shows refractive index change here, and this is the EGA, and what we see here that this is for nanoparticles, so the figure of merit it's compared to the GST, and this is the figure of merit of germanium telluride based nanoparticles, and this is thin film. And what we can see the change of the properties, and we see the improved of figure of merit for such nanoparticles. So now also some effects of thin film thickness on the thermal conductivity, because it's very important for the thermoelectric applications. And here we see this is the thick films, and this is the thermal conductivity of cubic and trigonal phase. This is the amorphous phase. So it's on the average like between 1.5 and 2. And if we reduce the size of the thin films, we can see also the reduction of the thermal conductivity. It's now less than 1 for crystalline and less than 0.5 for amorphous. So here, this is, you can see the table of 350 nanometer thick thin film, amorphous 0.3. Cubic 0.4, trigonal 1.67, and the size reduction we have the change of the thermal conductivity too. Also some switching characteristics of such ultra thin films. So the thin films also shows change in the resistance, as we discussed before. So here we see the resistivity and temperature for germanium antimony, and we see that it's lower than for thicker thin film, but on the same range as for the doped germanium antimony. Here you can see the integration of this 3 nanometer germanium antimony layer into the device, real device with titanium nitride and silicon, and so some characteristics like reset currents and the endurance here they all tested, and they found that current, reset current, it's changing the cross-sectional area of such device, and that the endurance, cycling endurance of such device is also like 10 to the 4 cycles, set reset. Nice also difference between low resistance state and high resistance state. So such very thin layers, ultra thin layers, they have also potential for rapid scaling of PCM devices. So here I would like to conclude my talk. So what we show today, what I showed today, the nanoparticles, they show good crystallization behavior for dimension on down 2 nanometer. They showed also increase of TC, the decrease of nanoparticle size, and decrease of melting temperature, the decrease of nanoparticle size, and similar switching characteristic was prepared by conventional thin film deposition techniques. Nanowires, also they showed reduction of melting temperature, shortening of incubation time for recrystallization, reduction of activation energy for recrystallization, and reduction of switching currents and powers in PCRAM devices. Thin films, here we observed increase of TC with reduction of thin films, increase of activation energy for crystallization with reduction of thin film thickness, then crystallization here for dimensions down to 2 nanometer. The optical properties like transmittance, refractive index, and excitation coefficient are higher for thinner thin films. And we also observed reduction of thermal conductivity for very thin films, and reset current scales with film thickness. So I think I would like to start with this part on the bonding and the size-dependent material properties. So if you have questions, please ask me.
Good morning, sir. Thank you for a wonderful session. Sir, I have one query about the metal insulator transition or metal transition. Is there any dependence between the size of particle or the size of the thin film with the metal insulator transition? Because in one plot we have seen there is no trend between we are going for so many thicknesses.
Yeah, this is very interesting question. I think there are not so many studies on that. There are some study on the growth of very thin film of germanium telluride, and a particular thickness like less than 1 nanometers, they lose this metal-valent bonding, and so they change the properties. So. And also there are recent reports on the change of vibrational properties of such phase change films, and also changing in these bias distortions. So I think there should be some effects on metal insulator transition.
And one more thing, in IR transmission application, IR rise transmission application, is that amorphous having higher transmission than crystallized phases for a case of IR also?
If you look to the, I think this transmission, yeah. So here this is the size of 7.5. Yeah, okay, so it's not measured, I think. So if you go further, but there is, so if you look, like this is the 40%, and here for 7 so 40, and this is like a little bit larger. So the amorphous, they are also more transparent, of course, yeah, it should be.
Else is anything in doubt? If not, then we can go ahead. We are running behind the time also. So just then we'll stop here. We'll have a break, short break, okay, and then we'll start next session quickly. Okay. So probably tea is there because you just have a tea is there. So just have a short break and then quickly come back. Then we'll start our next session. Thank you.